In the last lecture, we have learned how to the principles of the WKB analysis. And just to have a little summary, we dealt with an equation that has this form, right? And we want to calculate or to find out y in power series of epsilon. Where this, as I showed you last time, this is completely generic. This is every second order homogeneous differential equation linear may be mapped to this form. Now, just to establish the connection, if we have a function like that, then you can easily recognize it as a Schrödinger equation. Okay? So we can say that the Schrödinger equation mapped to this form for future use, what we are going to do, let's define epsilon squared as h squared over 2m, okay? And then we multiply all this by minus 1, so we have epsilon squared phi double prime is equal to, this is becoming minus, so I have v of x minus e phi. So actually Schrödinger equation mapped to this, the time independent Schrödinger equation, right, is mapped to this equation if q of x is v of x minus e and epsilon squared is h squared over 2m. Okay? This is just establishment of the connection between the two sides. Good. Now, what we have shown last time is that the solution for this may be written as y is equal to, or asymptotic to at least, when epsilon goes to 0, we can write it as e to the 1 over epsilon times sum from n equals 0 to infinity of epsilon to the power of n times Sn. This is what we did, which implies that it may be written as e to the 1 over epsilon S naught plus S1 plus epsilon S2 and so on and so forth. And if it so happens that S2, if we are interested in if S1, S2, S3 and so on are not diverging functions, logarithm, but are order 1 things, right, then we can quite safely cut the approximation here, which is the optical physics approximation, and calculate S0 at S1 and S1, which is what we did last time. And we find, finally, we arrived at y is proportional to some 1 over q to the power of 1/4 e to the plus minus 1 over epsilon times the integral up to x of s of square root of q, let's say t is not good. T will look like time. S is not good because I'm using S here. X is not good because it's okay, I will call it
Small q.
Small q. No. It's not analytical mechanics course. Small q exists only in the realm of Hamilton-Jacobi equations and things like that. Nobody else is using small q. Okay, so I give up t. This has nothing to do with time. It's just a parameter. Okay, this is what we obtained last time. Now, so, and we want to use it. Okay, so what's the simplest okay, what will happen, let's say, right? Okay, so what will happen if we will try to implement this equation, this solution, to the Schrödinger equation? Okay, note, so you see what Q is. So I will write in the most general case, in the Schrödinger case, that Y is A over V of X minus E to the power of 1/4, okay, times E to the plus 1 over epsilon integral up to X of V of T minus E square root dt plus B over V of X minus E to the power of 1/4 times E to the minus 1 over epsilon, this integral square root of V of T minus E dt. Right? This is the most general WKB solution of the Schrödinger equation. Okay? This is has to be, or we hope it will be, good approximation when epsilon is going to is relatively small. Okay? Are you with me? Good. Now, right, so for example, if you have an electron, right, this is V of X is Q times the potential. So let's say the potential is 1 volt, then this is 1 electron volt, 10 to the minus 19, right? Here the mass of the electron is 10 to the minus 31, but 8 squared is 10 to the minus 68 or something, right? So this is still very, very small, okay, with respect to that. Good. So this is the most general solution, and the question is now how to implement it. A few remarks. First of all, what about the lower bound?
Doesn't matter.
Doesn't matter. Yes, because what? Because I have e to the integral from, say, a to x, some function of x of t dt. This is e to the f, where f is dou f dou t, so this will be f of x minus f of a. So the e to the minus f of a may be absorbed into the capital A here or capital B here. You see? So I can, without loss of generality, I can put here whatever I like. I leave it now blank, but I can put 0, I can put every number. Doesn't matter. Good. Now, can I implement that in order to find the eigenvalues, the eigenenergies of a quantum system? This is, in many cases, this is our ultimate goal, to find the eigenenergies of a quantum system. So let's try to implement it. Before doing that, you can now see that there are two important regimes here. What they are?
E bigger than B.
Very good. We have two options. This one is written most naturally when V of X is larger than E for all the relevant values of X. What are we going to do if V of X is smaller than E?
You just get complex results in the integral.
Exactly. If V of X is smaller than E, then we can invert these guys and put an I outside.
And because it's a complex wave function, that's fine.
Yes,
Okay.
very good. So to begin with, let's try to deal with the following question. I have, this is V of X, and this is X. This is X equals 0, and this is X equals L. And here I have whatever potential you like. Right? The red is the potential. Now, to make my life happier, I would like to put the energy above the maximum potential. If my energy is above the maximum potential, I am always where? Right? Here I have e to the 1 over epsilon square root. Here I have e to the I over epsilon. This is square root of v minus e, and this will be square root of e minus v. Which of them should I use for this problem?
E is bigger than the second one.
The second one. Good. So I can write safely that y is a. Now, should I make anything here?
Yes.
Not so much, because although I'm changing I will write y, a, divided by the square root of e minus v, which is positive, not square root. E minus v to the power of 1/4. Now we are saying, well, I should have here also minus 1 to the power of 1/4, but I don't care because the minus 1 to the power of 1/4 may be absorbed into a. So my solution is that e to the I over epsilon, I over epsilon, the integral up to x of the square root of e minus v dt plus b over e minus v of x to the power of 1/4 again times e to the minus I over epsilon, the integral up to x of the square root of e minus v dt. Okay, this is the most general solution because e is larger than v all over the interesting region. Okay? Now, you already know that I can write now I can write y in a much simpler form, I guess, which is a over e minus v of x to the power of 1/4 times sine of the integral I of sine of 1 over epsilon, the integral up to x of the square root of e minus v dt plus some phase phi. Because this is always true. E to the I something plus e to the minus I something is sine something plus sine something plus phase. So now the two constants are not a and b, but a and the phase. Strictly speaking, I should avoid the use a here and use something else because, okay, let's call it c. Why? Because this and this are not the same constant. But it's just a standard thing of writing a e to the I something plus b e to the minus I something like sine plus phase or cosine plus phase or whatever you like. Good. Now I would like the most important thing is that because I analyze the system in power series of epsilon, not in power series of not small x but small epsilon, I can use this to get an approximation to solve a boundary condition. What are the boundary conditions in my example?
Phi 0.
What?
y0.
I want y of 0 to be equal to y of L to be 0. And now the question is, what are the allowed energies? Right? I have En. I have many energies. What are the allowed energies that satisfy the boundary condition? Okay, this is very easy because it involves not this part of the expression, but only that part. You see? First of all, I want this y to be 0 when x equals 0. This is very simple. I will assume that phi is 0, and I will put the lower bound here to be 0. By the way, again, by the same token, as before we say that the lower bound here is what determines 8, here you can say that the lower bound here is what determines 5, because you can always change 5 such that it will compensate for changing the lower bound. So, what I did now, I satisfied one boundary condition, which is
X equals 0.
that at x equals 0, I have the sign of 0. So I have another boundary condition to satisfy. What is that? 0 at x equals L. So what this implies?
That everything inside the sign is just phi m.
This implies that what I need is 1 over epsilon integral from 0 to L over the square root of E minus V of t dt will be equal to
Phi m.
n pi. Which means that we have a general solution for E. The energies, the eigenenergies of this quantum system will be what? Sorry, no, I don't have because yes. What do I need?
You need to integrate the
I can call this En, and now I have to integrate. So now I first have to integrate, and then I can solve. A case that I will be able to solve immediately is a case where V of x is 0. So standard potential well, something like that. Okay, infinite potential well from the course in the one, how do you call it, modern physics, right? So if this is the case, if V of x is V of t is 0, what I have here is square root of En over epsilon times L, right? Because there is nothing in the integral, but constant. This must be equal to n pi, and this implies that En will be equal to epsilon squared n squared pi squared divided by L squared. And now, if I plug epsilon h bar squared over 2m, I will get h bar squared pi squared n squared over 2m L squared, which happens to be the correct solution. It's just a miracle, right? It's not. It's an incident that this is the exact solution. But it so happens that for infinite potential, well, the WKB yields the exact solution for the eigenvalues.
How did you solve the integral?
I decided that V is 0. So here I have square root of E. Square root of E is a constant, it goes outside, and I have an integral over nothing, which that gives me L, just the length.
For every potential that don't depend on the location, you have the correct solution. Right?
Of course. If it is constant, then also a correct solution. Okay. Now, and now if I don't know what V is, then I have to solve this integral and this will give me the correct answer. Okay. So fantastically, apparently, we have a way to solve for the eigen energies of any one-dimensional quantum problem. Okay. What limits my ability to use it?
The ability to solve the integral. The ability to solve the integral might badly.
That's not a big deal. At least numerically you can solve it quite easily for any reasonable potential. Okay, so first of all, this miracle that it's exactly the eigenvalues is a miracle. And by and large, if you put here something like, some potential like that, I don't know, and you calculate the energies, you find energies that are not exactly the correct ones. However, the approximation will become better and better the higher is the energy. Because the higher is the energy, the more reasonable is the assumption that epsilon is small. I mean, the smaller is the epsilon. So for the higher and higher energy, you get better and better approximation. But even for the lower energies, usually it is not going to make horrible mistakes. I mean, you will be like 10% off the correct number. Yes?
You have a problem when the boundary layer is not thin like this. Like you have a thickness. And the boundary layer.
What you call boundary layer here?
Y of 0 equal 0.
Okay, so maybe we are speaking about the same problem. However, the whole story breaks down completely if I have something like that. If this is it. Why?
You're not in the same regime.
Or because the phase.
Because now,
You have to solve
first of all, here I should use the positive, and here I should use the negative with the I.
So you'd have some sticking condition?
But it's even worse because what's happened here?
Here's the dissipation.
Here, the denominator here is 0, so I have a divergence. So there is no way to implement WKB at this point and at that point. And by the same token, if maybe this is what you were referring to, if I would like to know what are the eigen energies of the harmonic oscillator, right? Then I would like to solve the equation, and this is E. But since I have to solve the equation with the boundary condition y at minus infinity and y at infinity is 0, I will get again. The regime is include these 2 points, right? And in these 2 points, the WKB diverges. The WKB asymptotic solution diverges, and because of that, I have no way to connect the right boundary condition with the left boundary condition. You see? So this is our problem, and this is what we are going to deal with during the rest of this lecture. So the question is, how to implement WKB in cases where there are points in the along the trajectory or in the region where we want to solve, there are points in which V of E is equal to E. V of X is equal to E. Okay. By the way, do you know what's the name of such a point? Turning point. Very good. This is a turning point. Why? Because classically, you know that if you have a classical particle with this energy, it will go like that, go, reach this point, and will go back to here, and go back to here. These are the points. This is the square root, right? The square root of E minus V of X. What is that? This is the total energy. This is the potential energy, right? So this what in the square root is a kinetic energy. It's yes. If you have a particle with mass 1, this is p squared. So this essentially is p. Okay? This is the momentum of the particle, or the velocity, if you write, if the mass is 1, and the velocity is 0, of course, at the turning points. So our analysis from now on, our efforts from now on, will be to analyze the WKB problem, to solve the same kind of problems implementing WKB when we have turning points in the which is usually the case, right? Good. So now we want to analyze WKB with turning points. And to begin with, we will start with, okay, so we are interested in WKB with turning points. And this is going to be this is a complicated task, but extremely nice, right? If as I told you in the beginning of the semester, there will be about 3 lectures that will have heavy mathematics, and where the tricky point will be to get a perspective, not to go through the little thingies, but to get a general perspective of what we are doing. So this is the last one, I hope, that have these characteristics. Maybe the next one will also. Okay, so we want WKB with turning points. And to begin with, actually the main, we can, I guess that I will erase this because I have no other choice. No one has invented yet an infinite whiteboard. So I begin with a single turning point. Okay, what is a single turning point? Let's make ourselves clear. We have, so what I'm going to plot here is V of X minus E. So this is our Q. Remind you, this is our Q. Oh, I have erased it, but this is our Q, V of X minus E, as a function of X, right? And I will do that. I will be nice to myself, and I will do that such that the turning point, which is a point where Q is 0, is exactly at X equals 0. Just to later we will move it to A. But for the moment, we have turning point. We took a function.
Is it a saddle?
What? No. I hope not. It's important. I hope not. This is a generic turning point. Okay. In a generic, I will, okay, if you are asking, by and large, Q of X will be, okay, it at X equals 0, Q equals 0. So I can write Q of X as AX plus BX squared plus CX cubed and so on. And I assume that A is not 0. Right? If it was a saddle, then A was 0. But this is extremely rare. Right? So I assume that A is 0. Are you with me? Good. So that A is not 0. I assume for the moment that A is not 0. Good? Fine. So, how do I remind you that we had when we dealt with generic boundary layer problem, we discovered that if A of x switches sign, right, inside the region we are interested in, we are going to have a problem. The solution to that is very similar to what I'm doing now. I see no point in doing it twice, and I prefer the WKB version of it. So what we are going to do now is asymptotic matching. The same trick that we were using in boundary layer problems. So first of all, I will look at this region. This is the outer region. Where, what is the outer region? It's a region where x is farther away from 0. How much it should be farther away? It's a good question. Let's, for the moment, try to, okay? So, in the outer region, I can write y outer, right, as, okay? So now we have A over Q to the 1/4 times E to the 1 over epsilon, because in the outer region Q is positive. V is larger than E, so we use not the I things, but the no I, right? Q is positive. So I have the integral up to x of square root of Q of t dt. Now, what will be the, first of all, what is the lower bound here? Whatever I like. As we said, it's just a redefinition of A. And so I'm taking it to 0. It doesn't matter. Although I cannot continue the solution to 0, I can still put 0 here because this thing is not what blows up, right? This is completely fine. At 0, my problem at 0 is with the Q to the power of 1/4. Now, what will be the other solution?
Just without the I, or with the
Minus.
Same thing with the minus. Which of them I should choose?
The one that's not divergent.
Of course, if this is now going to infinity, and quantum mechanics telling me that at x goes to infinity, y should go to 0, so I should choose a minus. So instead of writing it, I'm choosing this one, and I'm taking the b e to the plus to be 0. Right? So this is the outer solution. Are you with me? Please try to concentrate because you can very easily disappear. Okay. So all I did now, I wrote bluntly the WKB approximation. I only threw the one that diverges at infinity, and this is fine. Okay? Now, what about the inner solution? What will be the inner solution? Okay? Now, the inner solution contains the 0. So I cannot use WKB. However, in the inner solution, I can approximate Q of x by its leading order. Right? The idea is that x is small. If x is small, I can approximate Q of x by its leading order. So, in the inner solution, the equation will be, what will be the equation? The equation will be epsilon squared y, y double prime is ax y. in the inner solution regime. In the inner regime, I can approximate Q of x by AX. That's why it's an inner regime, because x is small. You see? Good. Fine. Does that look familiar to you? It's airy. It's airy. Up to whole lot of constants. So let's make it honest to God airy. How are we going to do that? I will define x tilde as x over gamma. Gamma, some parameter that I will choose immediately. And then d dx is 1 over gamma d dx tilde by the chain rule. So this equation will take the form epsilon squared y double prime over gamma squared. You see why I have chosen, now this is y after is a function of x tilde, right? And derivative of this is a derivative with respect to x tilde, like what we did in the boundary layer, is equal to a times x. But what is x? As x is gamma x tilde times y. So I can collect all the garbage to the left, and it gives me epsilon squared divided by a times gamma cubed y double prime equals x tilde y. And in order to make this one exactly airy, what I should do?
1.
I should choose gamma such that the coefficient here will be 1. So now I know that gamma, very important, gamma is what? Gamma is epsilon to the 2/3 divided by a to the 1/3. Because then this implies that gamma cubed is epsilon squared over a, and then I have 1. You see? So this is gamma, and now that I know gamma, I know what is the relationship between x and x tilde. And after doing that, I have y double prime equals x tilde y. So I know what is the solution in the inside regime. What is the solution?
It's just area of x.
Y in, right, is c times area of x tilde plus, let's call it plus
C1, C2.
C1 times area of x tilde. Okay? So I have the inside solution and I have the outer solution. Okay? Now, what is my next mission? I should match them. Do you believe that this will match with that?
It would be a pain, but sure.
Hmm?
It's going to be to do it.
Okay, now, how are they going to match? So we will check. But first of all, A and B, whom I should try to match?
One of them diverges.
Okay, what are the conditions under which I will match them? The matching,
For x tilde is small.
yes, of course epsilon is small, epsilon is going to 0,
No, x tilde.
but the matching, I have to match that y outer at x goes to 0, right, with y inner at x tilde goes to infinity. This is the matching regime, right? X tilde is very large, x is very small. So an immediate conclusion is that if I have any chance to match them on Earth, I should require the Bailey to be 0, or the coefficient C1 to be 0. That's why I call it C1 because I didn't want to waste a letter on it, right? Because the Bailey diverges, so it cannot match with anything. The area is going to 0, so that's fine. Okay? So, this is my goal. I have to look at the outer solution as x goes to 0, and I have to match it with the inner solution as x goes to infinity, x tilde goes to infinity. Good. So, what is the outer solution as x goes to 0? Please.
Zero.
Zero.
What?
A over Q.
No. X very small. I don't put S. Of course it will be 0. I'm not sure that it's 0. Why are you saying
No.
No. X is very small. Right? I should. Okay. X
No, sure.
much smaller than anything, and this is X tilde much larger than anything. Okay?
So you have. Does the integral just pop out? Because you have.
What? Okay, let's see. I have A, okay, divided by Q. But when X is very small, Q is A to the 1, Q to the 1 quarter is A to the 1 quarter, X to the 1 quarter. You see? Okay? And now I have E to the minus 1 over epsilon. And now I have to integrate over Q over square root of Q. But what is the square root of Q? It's a square root of AX. So I have square root of A here. And I should integrate over square root of X from 0 to X, which is 2/3 X to the 3/2. You see? This is the outer solution. And now the life appears a little bit nicer to us. Why?
That's Airy.
Because this is a form we know that the Airy, the asymptotics of Airy, looks like that. Right? Okay. So now let's go to the in. We have C. Now what is the asymptotic of the Airy? Okay, remind you. The asymptotic of area of x is asymptotic at large x to e to the minus 2/3 x to the 3/2 divided by x to the 1 quarter, and I will put here square root of 2 pi. Why is that? Because all the analysis we did for the area was, let me just make sure that it's square root of, I'm not putting the square root of 2 pi in the wrong place, although it doesn't matter by the way, but
It's just a constant.
I hope it's the right, yes, or maybe it's 2 square root of pi. Why I don't have it written here?
זה 2 שורש פאי.
Hmm?
זה 2 שורש
Yeah.
פאי.
Okay. So 2 square root of pi. So this constant have absolutely no importance to what we are doing. However, I wanted this area to be the correct area that you find in the books, right? And all the analysis we did for area, the local analysis and blah blah blah, was for the linear equation. So you can multiply it in whatever you like. In the book, they are using, in the standard area functions, they are using some sort of a normalization that implies that this is what should be written here, right? But otherwise, it is that. However, we don't want to put here x because we are dealing with the asymptotic of x tilde, right? So what I'm actually interested in is that asymptotic of area of x tilde as x tilde goes to infinity. So okay, so here, this is that. I just put a tilde on the x. Now what is it? Now let's translate it back to x, right? And how we are going to translate it? Very simple. X tilde is x over gamma. So x tilde is x times a to the 1/3 divided by epsilon to the 2/3, right? X tilde is x times a to the 1/3 divided by epsilon to the 2/3. And we want to plug it here and here. Very good. So area of x tilde of whatever x, right? Or I can write it as y inner is approaching to what? So we have 1 over 2 square root of pi. And we have here c. Sorry, there is a c I forgot. Just a constant. Constant over 2 square root of pi. And now we have down here we have x tilde to the 1/4. This will be x to the 1/4 times a to the 1/12. Have you ever seen such a power in your career? Right? A to the 1/12 because it's a cubic root to the power of 1/4. And here I have what? Here I have epsilon to the 1/6 because it was 2/3 and I took the 1/4. Very good. And now what about the exponent? So in the exponent I have e to the minus 2/3 times x to the 3/2, and now I have a to the 1/3 to the power of 3/2, which is what? Square root of a. And downstairs we have epsilon to the 2/3 to the power of 3/2, which is epsilon. Now here is the impossible thing happened, i.e. this and that are exactly the same.
But is it a coincidence?
Hmm?
It doesn't seem like it.
No, it must be like that because they have to match.
Yeah.
If it isn't that, then we cannot match them, right? So this implies that this and that have a match. Now, what about the coefficients? So the x, we have another matching. Here we have x to the 1/4, and here we have x to the 1/4. They also match. And what about the rest? The rest are constants. All the rest are constants. So we can now say that we know what C given A. Okay, we know that C is equal to 2 square root of pi times A times epsilon to the power of minus 1/6 times A. This is a semi-grand goal of this part of the calculation. So you see what's happened. We started here with an A, and we were able, by matching the inner to the outer, yes, and we assume, of course, that there is a region here in which both approximation hold. This is a matching region. We are going to have to check it later on. But for the moment, I want to continue with that. Good. So, once this is given, okay, what is my next goal? The other side, right? I also know that I have another solution in, what color should I use? This. In this region, which is also outer in the sense of I can implement the WKB, right? Now, what's the difference between the WKB here and the WKB here?
I.
The I, right? So I can, here in the purple region, so we have y outer, let's x larger than 0, and now in purple I will write y outer at x smaller than 0, and this is say b to the divided by q to the 1/4. Okay, again, now, okay, maybe I will be more, I will write it as minus q to the 1/4. Minus q now is positive, right? Minus q is e minus v. Okay, I added a minus here, so I should multiply everything by minus 1 to the power of 1/4, but I absorbed it into the b. And now I have sine of 1 over epsilon integral from, okay, now I will do it from minus x to 0 of minus q of t dt plus phi, right? Where again minus q is e minus v. This is the outer one. Okay, where I use the freedom. I took the liberty to, I have e to the I something and plus e to the minus I something. I took the liberty to write it like that. Okay, fine. And again, putting this as a lower bound and the 0 up is like changing the phase. So again, I would like to match, but now I have to match it to something very special, which is the 80. This should match here. It should match the same 80. It's not a different function now, right? Because all over the inner regime, the answer is 80. 80 allows me to cross the 0, to cross the Rubicon, to go from one side to another. So now I have this, and I should match it to the same area, but now for x negative. So I should open the books, find what is the asymptotics of area when x is not large and x tilde is not large and positive, but large and negative, and match it with that. You see? Okay. Let's continue. So I should open the holy books and ask for the asymptotics of the Airy function okay. Okay. So looking at the books, we find that this is y in as x much larger than 1. Now I am writing y in, same thing, as x tilde, let's say, much smaller than minus 1, right? Large negative values. Do you remember what's the difference in the Airy between the positive and the negative? Just to remind you, the way Airy behaves, right? The Airy is doing something like that, right? But here, it oscillates. Okay? So the asymptotics of Airy at large negative values is y in equals to c, it's the same c, right? You cannot have different coefficients. Divided by square root of pi. Here we have 2 square root of pi, but here we have square root of pi. Again, these are have to do with the way people are normalizing the Airy function. It's not essential, and you can replace it by anything else. Now we have 1 over x tilde to the power of 1/4. And not x tilde minus x tilde. Minus x tilde to the power of 1/4, right? Because x tilde is negative, so I need the minus. And I have sine of 2/3 minus x tilde to the power of 3/2 plus pi over 4. Okay? And we have to this, after replacing the x tilde by x according to the prescription we already have, okay? This will be y in is c over square root of pi, and now I have 1 over minus x to the power of 1/4 times a to the power of 1/12, and here we have epsilon to the power of 1/6, right? Same thing as before. Sine of 2/3, and here I have a square root of a over epsilon minus x to the 3/2 plus pi over 4, right? So this is y in at x tilde, there it goes to very large negative value. And this should match to what? To the outer. Now, what is the outer? Not the outer when x goes to 0. So I can replace the q by ax, right? So for the outer, for the y outer, when x goes to 0 means that q is replaced by ax. Q is replaced by ax or by, yes, this q is replaced by x with a minus, right? The minus is built in. So what I will have is b divided by a to the 1/4 times minus x to the 1/4 and I have the sign of 1 over epsilon, and now I have, so there is 1/2 here, of course, it's the square root, right? So I have square root of a, and I have the integral over, and I have minus x to the power of 3/2 times 2/3 plus phi. Okay? So, we have to match this to that. How are we going to do that? So, first of all, this is exactly that. Again. So we have one important thing, which is the matching implies that phi is what? Is pi over 4.
And, what about B?
Oh. Now I can say that I have this x to the quarter is the same of this one. So the other thing I have discovered is that B is what? Is 1 over square root of pi times c
1 over a to
times epsilon a to the power of 1/6. By matching this with that. Okay? And this is very important because what we found now is a relationship between B and A. So that's a trick. You see, we have the WKB solution here and the WKB solution here. But what are the constants? We need the coefficient in order to solve the boundary value problem. Okay? So we have established a connection because now what C is, we have calculated it there. It's 2 square root of pi times a epsilon to the minus of 1/6. So what is the connection between B and A?
You just
Hmm?
שתציבים את הקבש לקבועי.
1/2.
2, right? You can find out very easily that B is 2A. And by the way, we have also another constant that has to do with the phi, is pi over 4. Okay? In that way, the WKB solution crossed the Rubicon between this and that through the region, which is note that if you just want to amaze or to amuse yourself, that what we did here is an asymptotics of an asymptotics. Because first of all, we assumed that epsilon is small, and we did asymptotics. And then we assumed that x is small, and this is another asymptotics, right? And matching. Okay, but at the end of the day, we cross the Rubicon, and we find that. What all this is good for? What is our goal?
Finding the energy.
Our goal is to find, for example, the eigen energies of the harmonic oscillator or any other potential, but is that something that we can use to find the eigenvalues of harmonic oscillator?
Not necessarily. Yeah, sure.
Okay, let's plot for ourselves the potential of the harmonic oscillator. Right? Here is x. Here is v of x. Here is e. Right? So, in terms of what are the turning points here?
Minus x squared.
I have this one, let's say A, and this one B. Now, all the manipulations and all the hand waving that I did until now were to make contact between the WKB solution here and the WKB solution here. But in order to solve the problem with boundary condition and plus minus infinity, I have to continue and to do that. However, this is just a mirror image of that, essentially. Okay? Not necessarily, I mean, you can have non-symmetric potentials. It's not a problem. But the question of the matching is the same question. Okay? So now I will forget about the fishy things that I have to do here and to do here in order to match the WKB. And I will look at what's happened only to the WKB. So I forget about the inner solution. Right? So, what can I say? First of all, here I can use exactly what I did, except that I will replace 0 by A. That's all. Okay? And I will find that the solution here, in this region, again, farther away from the turning point, okay, is y, let's call it y right. Y right is what? Is b over square root of e minus v, not square root, 1/4. The 1/4. Okay, no, I don't have enough room here. I should move to here. Y right is b, but okay, doesn't matter, divided by e minus v of x to the power of 1/4 times the sine of 1 over epsilon integral. I'm just taking the purple thing here, right? I copy it. The only difference I'm going to do is to change the limits. Instead of minus x and 0, it will be x and a. Right? Because a is a new 0. Okay, x and a times the integral over e minus v of x, v of t, sorry, dt, plus phi that we determine to be pi over 4. Close parenthesis. Okay? This is a solution that should hold in which region?
Inside.
Hmm?
To the left.
All the inside region. So this solution, the y right, start here and will go to here until it will stop here somewhere before the next turning point where it blows up again. Okay? By the same token, I could now, what about if I will start here? Right? I will start here. I will take here the exponentially decaying solution, and I will match here to the Airy, and so on and so forth. It will give me exactly the same results. No matter, I mean, it's not. It doesn't depend on the symmetry of the potential. I can do it for non-symmetric potential. Doesn't matter. All what I did, because I didn't specify v of x, right? So I can write y left. Y left will be d, say, divided by e minus v of x to the power of 1/4, sorry, sine of 1 over epsilon, an integral over square root of e minus v of t dt, plus pi over 4. My only problem is the limits, right? So again, to make things I should have it in different color, but to make things positive, I will do that from b to x. Okay, so this is y right, this is y left, and of course the difference between them are the limits here, and here I have b and here I have d that are arbitrary constants. Good. Now, however, these two solutions, one of them I've started here, I overpass this turning point and find the solution here. For the other one, I started here, overpass the turning point, and find the solution here. But they should be the same solution. You see? Instead of calculating everything up to the other side, up to minus infinity, and requiring it to be to satisfy the boundary conditions, I tried from this boundary condition and from this boundary condition, and I calculate it until the middle, and now I want these two to match. Where? Everywhere here. Everywhere here in the blue region, this one and this one should match. How come?
So it's just a matter of constants? Using B and D?
No, B and capital B and capital D. No, you have a different functional things here. Okay, so now here is the big trick. Here is the trick. Yes, no, I will continue from here. I would like to write this as d over e minus v of x to the power of 1/4, which is the same, so d, yes. And now I will write it as sine of 1 over epsilon. Now I have an integral from b to x. Okay? Please allow me to write it as an integral from b to a on the square root of e minus v dt. Right? Minus the integral from x to a over square root of e minus v. You agree? This minus that is exactly this. Right? I integrate from here to here, and then I subtract it from here to here, and I get the same. Okay? Now, there is something I've forgotten, are the phases, right? So what I will do, I would like to write here minus pi over 2 plus, minus pi over 4 plus pi over 2. Because this is pi over 4. Okay? Aha. Here is now another magic. Yes, today with a lot of. What's that?
Needs to be plus pi over 4. Oh no, it's minus.
Minus.
It's just minus y. The thing in y.
What is here is exactly minus of what is here. You see?
So if they
In the the red square, right? This one and this one are the minus of each other. Okay. So, what I should do in order to make the two solutions match?
it's inside sign, so just say this one.
But sine of minus x is minus sine of x. So, as long as this, what remains, is equal to n pi, as long as this is equal to n pi, I can choose d to be either plus b or minus b, and this will allow me to have the same solution. Do you see that? Right, so for example, if this plus pi over 2 is equal to 2 pi, right, then sine of something plus 2 pi is the same thing, is the sign of the same thing, but this is the sign of minus, so it will be minus. So if this plus that is 2 pi, then I need d to be minus b. And if this plus that are 3 pi, then then d is b. So by and large, I can solve everything. Wow. Okay. So after all this blood, sweat, and tears, we discover that I want to keep that. After all this blood, sweat, and tears, we discover that I can match the right and the left solution, right? If 1 over epsilon integral from b to a over the square root of e minus v of x, v of t dt, of x, now I can write x because the boundaries are b and a, plus pi over 2 is equal to n pi. For the even ends, d must be minus b. For odd ends, d is equal to b. But the matching is fine. Now, what are the possible values of n? N is 1, 2, 3, and so on. N equals 0 is prohibited. Why? Because this integral is over e minus v, which is positive between b and a. So this is a positive quantity, and this is a positive quantity. I cannot have 0. I can have only 1, 2, 3, 4. And so on. So this is En now. It's the nth eigenvalue of the problem. Okay? So what? So I can write it in a different manner as 1 over epsilon integral from b to a over the square root of En minus v of x dx equals to n plus 1/2 times pi, where now n is going from 0, 1 to blah blah blah. The same, I just move the pi over 2 and I change it. Instead, I mean, here it was, the first one will be 3/2. Here the first one will be what I wanted to say. N plus 1/2 or n minus? Maybe n minus 1/2?
No,
It's plus.
3/2.
Yeah, it's plus. It's plus and we can start from 0. Okay, so, what's eigenenergy? Let's look for the harmonic oscillator. Okay, so in the harmonic oscillator, we have V of x is x squared over 4. The 4 is when we calculated the perturbation theory, we also use 4. Okay, you can have whatever you like. So if V of x is x squared over 4, right, then what? So I'm solving y double prime times epsilon is equals to x squared over, q is what? Q is b minus e, yes. So x squared over 4 minus e. Y with the boundary condition y plus minus infinity is 0. Right? That's an harmonic oscillator. So what are the turning points? Given E, what are the turning points? The turning points are where E is equals to x squared over 4. So the turning points, x plus minus star, say, are 2 square root of E. Okay? So this integral is now 1 over epsilon, the 2 square root of E minus up to, of course it's plus minus, so up to plus 2 square root of E of x square, what I need E minus, so E minus x squared over 4 dx. This must be equal to n plus 1/2 pi. Okay? So now you only have to calculate this integral. By the way, do you recognize this integral? What is that? Yeah, of course. You can use it. I wanted to do that, but I have no time, right? I will just tell you that this integral gives you 2e times pi over 2. I mean, you can divide everything by e, and then you have 1 minus something squared, and then you define it as a sine and cosine and blah, 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 blah. And this integral gives you, this is 1 over epsilon times 2en. What I said? 2e times pi over 2. Okay? So that's the result of this integral. And this must be equal to z. So now I obtain that En is what? The 2 and 2 cancel. And we have epsilon times, and the pi cancels with that, right? So I have epsilon times n plus 1/2. And that's it, right? And sorry, yes. And when so these are actually the exact energies of an harmonic oscillator, right? You have to do the right manipulation with the Hamiltonian. So the Hamiltonian is minus 8 squared over 2m y double prime plus, here I have 1/2 m omega squared y is equal to ey, right? You see? And if I divide, I want to do what? So my epsilon is h. My epsilon squared is h squared. Epsilon is h over 2m. Okay? And now, here I have x squared y. Now, so I have to do some manipulations here. Right? And this yields, okay, I wasted all my time. And it's weird because I felt before the lecture that I will have extra time, so I wanted to start another issue, but for the moment we didn't end up with this one. Maybe I will spend some time next lecture. Okay, before that, what we obtained here, or in general, what we obtained here, right? This is what is known as as Bohr-Sommerfeld quantization condition. So the idea was, after Planck discovered that eigenenergies of systems are quantized, and this was supported by the discovery of the spectrum, of the discrete spectrum of the hydrogen atom, all the, you know, remember again, course of modern physics, Balmer series, and who knows what, Paschen, don't remember, right? So after all these discoveries, people realized that there is no way to, I mean, that things had to be quantized. But they didn't have yet Schrödinger equation. And what Bohr and Sommerfeld suggested at the time was a huge patch that they want to stick to the classical mechanics. Instead of just taking Newtonian dynamics, throwing it through the window, and replacing it by Schrödinger equation that they didn't know. Instead, they decided to have this patch over the classical physics. So they said, okay, classical physics say you can do whatever, every trajectory that go back and forth in the harmonic oscillator is fine, is legitimate, and every energy is legitimate, right? However, in quantum physics, they said you have to include only those trajectories that satisfy this condition, which is actually that the integral over the momentum, because this is the momentum, as I showed you, right? So the integral over the momentum, when you go back and forth, is they say it's n pi, not n plus 1/2 pi, but doesn't matter. It gives you the correct spectrum in many cases, right? Now, people were happy with that for a while, and this is what they, again, taught you in the modern physics course, I hope, that there is a Bohr model, what they call, and you calculated the eigenenergies of the hydrogen atom and so on, and this is actually the way it was done. Of course, they didn't extract it from the Schrödinger equation. They just suggested it as a possibility, and I think that people abandoned that because they tried to implement it to the helium atom that have 2 electrons, and then it breaks down. Okay, and they felt they don't have any access to the eigenenergies of the helium atom, of the 2 electrons, one nucleus with charge 2 plus 2. They felt they don't have so, and this was the motivation that led Schrödinger and Heisenberg to suggest their alternative. Quite interestingly, it turns out after many years that there was a technical trick that if they had they implemented that, they can have also corrections to the helium. They can also get the helium atom energy from such calculations. By the way, even the Schrödinger equation does not allow you to solve the eigenenergy of the helium atom because it's a 3-body problem. You have to do variational principle, right? Some approximation. So this is not worse than that, but meanwhile, there is a whole story here that I will skip, but essentially, this is a way to get this approximation from the Schrödinger equation. Okay, and it involved all this, trickery with the WKB, and again, for the harmonic oscillator, it gives you exactly the exact. That's the other miracle, right? That it gives you also the exact eigenenergies for the harmonic oscillator, but that's it. In other cases, it does not give you the exact solution, but you can still. It's still a very good approximation once you are going to high energies. Okay, So I think I have no other choice. I will stop here. There are a few things to add here. Okay, what I have omitted. First of all, it's nice to implement that to other potentials. I wanted to implement it to quadratic potential and so on. And you know that in the quadratic potential, the energies are going like n. N is linear in n. In infinite potential well, it goes like n squared. And in between, like if you have a quadratic potential, it goes like n to the, who knows, some power between 1 and 2, maybe 3, but I'm not sure. 4 quarters or something, right? So it interpolates between 1 and 2. It's interesting to see that. Even more important from the point of view of the math here is to analyze exactly what is a matching, what is the matching condition. But I'm not sure that it's worth spending, half an hour in the next lecture, so I guess I will skip it. If you're interested, it's okay, you see? All what we did is not enough for our cousins in the math department, right? You have to show that there is indeed a region here where you can do the matching.
Does that just mean that A is not 0? Does that just mean that A is not 0?
No, you have to show that the corrections from this are negligible at some finite region, at some region here that becomes infinitely wide as epsilon goes to 0. And you can find it in the book. It's very important. It has a lot of insight, but I don't think that I will waste a lecture on that. So I think that this is what we did with the WKB, and next time we are going to, we still have 3 lectures, right? So next time I still have to make my mind what I would like to do, but essentially what we have to, until the end of the semester, we have to learn how to approximate integrals, symptotic analysis of integrals, which is a very useful technique, but for some reason I don't like teaching it. It's very, very important, very useful. I don't like it. And the other one is two-time perturbation theory, which is quite nice. But okay, until next week I will make one. I will decide. Thank you.
I ask something about the exam. It will be an open material or it's a closed material?
I think it's closed.
Closed?
Yeah.
Completely?
Completely.
You have to remember everything in our head?
Last year it was closed material.
The same concept?
Yeah, with Nadab. I think
Okay.
this year, will be also with the closed material.
The second thing, can you give us extra days for the last exercise? Homework?
Homework 8.
Last one.
The last one,
It's 8 years.
it's till 14th of January.
14 years.
You have a lot of time.
Okay, so
You have 1 week. So
I think that's
no. I mean, because I publish it
okay.
this Sunday.
Yeah, 1 week. So
1 week from this day. So midnight.
my mistake.
That's okay. I mean, most of the methods, they are pretty much the same. The only difference is in the equations, but you see that you need to know some core stuff like dominant balance,
It's
like
the easier one.
WKB approximation, boundary layer theory. So just learn the algorithms, and then you can solve anything you
No,
want.
I'm afraid of complex integrals.
No, I mean,
To find the integral of something,
if
I'm not
some,
familiar with that.
I think Nadav will provide then what are the values. I think last year there was some tricky integral, but he actually wrote the what's the answer for this integral in the in the description of the problem. So don't worry about it. Just learn basics of the course and that's it. If you truly understand them, it won't be a problem. I mean,
It's technical things. And
yeah.
technical things.
Yeah, technicalities.
Oh, still is about the guys?
No, it's just a reminder, and I want to begin with the motivation. Why do we even need to use WKB instead of manually? Okay, it's time to start. So today we will discuss WKB theory and how we can implement it to solve very similar differential equations with some changes. Okay. So first of all, let me start with the motivation. Why do we need to use WKB theory instead of boundary layer? Okay. So for boundary layer theory, this is general form of the equation. Okay. And to find the formal approximation, you need to find outer solution, inner solution, then we do asymptotic matching and subtract it from the informal approximation. And usually, outer solution is some smooth, well-behaved solution, which is slowly changes, right? So this is outer region. And here solution is smooth and well-behaved. But here we also have small region where inner solution behaves different. In this region, if some thickness of epsilon, but sometimes you know that it can be epsilon with other power. So, but for this example, let us assume for the thickness of this region, inner region is epsilon. In this region, inner solution behaves differently from outer solution region. Why? Because in this region you have sort of a breakdown of this slowing solution, and in this region you have highly varying solution. Okay. So, and in this case we can implement boundary layer. So we know this. We can call this dissipative phenomenon. But sometimes we can have a global breakdown. So let's have a look at this equation. Epsilon y double prime plus y equals 0, and y of 0 is 0, y of 1 is 1. Okay. So first of all, this is second order differential equation with constant coefficient. Therefore, we know how to exactly solve it. Let's find the exact solution. So we have epsilon lambda squared plus 1 equals 0, right? And therefore lambda is plus minus 1 over square root of epsilon, and here is pi. Okay. So exact solution is C1 times e to the e over square root of epsilon plus C2 times e minus e square root of epsilon. That's a general solution, and then if we plug in these boundary conditions, eventually find exact solution in this form. So if x is 0, you can see that our solution is 0. If x is 1, you see that our solution is 1. So this is perfectly matches boundary conditions. And now let's have a look at what happened with this solution. Then epsilon goes to 0. It oscillates highly, right? So, that happened independently of x. So in this case, we don't have any small inner region in which there is some high oscillations of the function. For the whole domain from 0 to 1, we may have this oscillation as epsilon goes to 0. So that's why we call it not dissipative phenomenon, but dispersive phenomenon. And because of that, we, in a minute, we will see why we cannot use for this problem our well-known boundary layer. So we call this dispersive phenomenon. And just to make sure that there is some problem with boundary layer theory in this example, let's begin to solve it, and let's find out the solution. What is the solution for this problem? 0. Which is not great at all, right? So it's terrible approximation to the exact solution. So that's why you cannot solve problems like this when you have global breakdown. So where you don't have any small region. So and when epsilon goes to 0, you have so that your solution rapidly changes. So
What's the breakdown again?
breakdown, it's then epsilon goes to 0, your solution highly oscillate or very rapidly. So for example, here we only have it for inner part in a small region, and this is local breakdown. But here we have global breakdown. So independently of x, then epsilon goes to 0, and that solution highly changes. Okay.
So like the inner region is the old region.
So basically, whole domain is like inner region. So that's why you cannot do any asymptotic matching. So because the solution behaves for whole region like it was in inner region. So that's the point. Okay. So that's why we need to create something new, and some scientists did it for us. And they say that maybe it will be better to try to find solution for such problems with the global breakdown in the form of a of x e to the 1 over delta s of x. So they tried different approach. When we solve boundary layer problem, we usually assume that y of x is a power series of like this. But now we assume that our solution behaves exponential, not as a power series, but as exponential. And this solution valid for both real and imaginary function of s. So when s is real, we have dissipative phenomenon. So namely, for positive s, it exponentially grows. For negative s, it decays. And if s is imaginary, we have dispersive phenomena or oscillations. So like rapid oscillations, like waves, etc. Okay. So I think you derive all of the formulas for WKB. So derivation is quite simple. I think that I've shown you how we can rewrite any second order differential equation in the Schrödinger form, right? So that's why, without loss of generality, I can write any second order differential equation in this form. I mean, it should have some small parameter. So, and we assume that solution y of x is e to the 1 over delta s naught of x plus s1 of x plus delta s2 of x plus and so on. Okay. And in this case, we can show with dominant balance that delta is all delta epsilon. Okay. So, and for S1 S not S1 S2, you have this. So S naught of x. So if you plug this expansion to this equation, you finally end up with S1 plus minus integral of square root of q of t dt. Okay. Then for S1, you have S1 s1 of x is minus 1 over 4 ln q of x. Okay. And s2 of x is plus minus integral of q double prime divided by a q about 3 halves minus 5q prime squared divided by 32 q in about 5 halves. In the internal notes you also can find S3, S4 and S5. Okay, but usually we use only these three. Okay. And you can write easily general solution for second order. It's just I think you did it on the lecture. So let me skip this part and go to the conditions for validity. So let's discuss when we can use WKB and how many terms we need to use in this expansion to get a good approximation. So first of all, we need to say that our solution in this form has singular nature. Why? Because first of all, this series usually diverges, and therefore we need to find the good point where we can truncate this series. Second of all, these terms should behave as follows. So S1 has to be much smaller than 1 over delta S naught. S2 delta should be much smaller than S1. So basically you have to check if the next term is if the next consecutive term is much smaller than the previous one. Okay? That's
Delta S2.
delta times S1.
All the
Yeah, just take this expansion. So, yeah, you have to check it. But because we truncate the series, we need to also sometimes find what is the error, and we can find it. So WKB has a good approximation if the next neglected term, the next term that so for example we take the first two as 1 over delta S naught and plus S1. We need to check if the next term is small relative to 1. So if we take, for example, first n terms, we need to check that the next one, so delta to the power n plus 1 s plus 1 of x, this has to be much smaller than 1. If it's true, then WKB yields good approximation. If not, we need to take the next term. So, and we have two, basically in most of physical. Okay, thank you, Alex, for scaring me. So for most of physical problems, we have two different levels of approximation. The first one, we call it geometrical optics, and the second one is physical optics. So for geometrical optics, we just take the first term. So our approximation of solution is e to the power 1 over delta s naught of x. Of course, in most cases, it's not a good approximation, but in some cases it is. And the second one is physical optics approximation, in which we take the first and the second term. So 1 over delta times s naught of x plus s1 of x.
What's the difference between the two?
So physical optics approximation is usually preferred one, and it's much more accurate than geometrical optics.
Now we don't know which one is the.
Because you have geometrical optics, then you draw a light as some error. Like you have, I don't know, maybe have some lens and there's a light and you focus on some point F, right? This one of the descriptions, but true nature is much more, complicated than this. So, and with physical optics, you need to use take into account diffraction, diffraction. So that's why, because this expansion has more terms than this, we call it like geometrical. Okay. So, yeah. Now let's solve. So the first problem is called epsilon squared times y double prime plus epsilon squared y prime plus epsilon, plus y equals 0. As epsilon goes to 0, we need to find, with using double KV method, the first order approximation. Okay. So, as you may notice, it's not the same form as we have here. So that's why we can do two ways. First way is to convert this equation to this equation, as Nadav showed you, or we can just simply use this form and directly plug it in. So it's pretty much the same, but let's just plug in this form to this equation without convert this equation into a transitive form. So for y prime, what do we have? We have 1 over delta times s naught prime plus s1 prime times y of x. Okay? then y double prime is the same but squared, and plus second derivative of this, so 1 over delta s naught double prime plus s1 double prime times y of x. Okay, and now let's plug in these derivatives into this equation. So epsilon squared times
If you have 1 also? It's the, okay. No.
1 over delta square s naught prime squared plus 2 s naught prime s1 prime over delta plus s1 prime squared plus 1 over delta s naught prime double prime plus s1 double prime. This is the first term, then plus epsilon times 1 over delta s naught prime plus s1 prime, and the third term is plus 1.
Is it epsilon square or just epsilon? The y type.
Yeah, the square. Thank you. Yeah. Okay. Now let's. In this problem, delta is order of epsilon, and now let's group all the terms. So for epsilon, is 0. What do we have? We have from the first term s naught prime squared and plus 1. This is the first term, then plus first power and epsilon. We have 2 s naught prime s1 prime, this term. Then we have plus s naught double prime, and from this plus s naught prime. Okay. Plus terms with higher orders of epsilon equals 0. Okay, so and now we have to solve two equations. The first one is s naught prime equals plus minus e.
In the solutions, we always say that delta is equal to epsilon, always in the WKP.
When here you have epsilon squared, then delta is epsilon. But if not, you need to do dominant balance. But if, for example, here will be just epsilon, delta will be square root of epsilon. We can use this logic. So from the first bracket, s naught prime is plus minus I. So therefore s naught is plus minus ix. Okay, this is the first. You also can notice that s naught double prime is 0. And therefore this term is 0, and we only have to solve this equation. 2s naught prime s1 prime equals minus s naught prime. So s naught prime cancels out, and we have s1 prime equals minus 1/2. So s1 is minus x naught. Okay, great. Now we can write a solution in the physical optics approximation. So the solution is e to the plus minus I x over epsilon minus x over 2. I should write here as epsilon goes to 0. But we can check whether it's true or not. Why? Because again, this is just second order differential equation with constant coefficient. And we can solve exactly. So let's check. So it's epsilon squared times lambda squared plus epsilon squared times lambda plus 1 equals 0. Okay, so let's solve it for lambda. Lambda 1, 2 equals minus epsilon squared plus minus square root of, this is squared, so epsilon to the 4th, and minus 4 epsilon squared divided by 2 epsilon squared. Okay, now we can divide it by 2 terms. So minus 1, first minus 1/2, see? Then plus minus, and let's put this inside the square root. So inside the square root we will have 1 over 4 minus 1 over epsilon squared. Right? So because epsilon goes to 0, we can neglect this term with respect to this one and write it as 1/2, again, 1/2 minus 1/2 plus minus I divided by epsilon. And therefore, exact solution C1 times E minus x over 2 plus EX over epsilon plus C2 E minus x over 2 minus EX divided by epsilon. So I got the same one using double equilibrium. Again, because here I wrote it approximately to, we can use get more terms here to match it with this one, but at order of epsilon we have the same result, which is great. Now let's consider 2 other equations. Epsilon squared y double prime of x equals sine of x times y of x. So this is the first one, and the second one, y double prime x equals sine of x squared. times y of x. So for the first one and for the second one, we need to say for each fixed values of x, physical optic approximation is good as epsilon goes to 0. That's the first question, and the second question is WKB accurate, then x goes to infinity. Okay. So first of all,
What is the second question?
is WKB theory for these equations is accurate, then x goes to infinity, or we cannot use it. That's the second question. So to understand whether physical optics approximation is a good one, we need to see whether the next term of approximation is much smaller than 1. Okay, so namely we need to check delta S2, is it much smaller than 1 or not. So if it's much smaller than 1, we can say that the approximation of physical optic approximation works good for this. Okay, if not, so we need to take more terms. Okay, so we need to basically check if this is much smaller than 1. Okay. So what is the equation for S2? So for S2 we have this, right? This integral. So will this integral be always much smaller than 1? For, in our case, q is, so in this case q of x is sine of x, and the second case q of x is sine of x squared. So what do you think? I mean, we can plug in q of x, find all the derivatives, and calculate these horrible integrals, but maybe we can analyze it without integration. So again, we need to think whether S2 times epsilon.
So always isolating with sin x.
Yeah, I mean,
You don't have a
but sine is is limited between -1 and 1.
Yes.
Okay.
So it can be -1 or 1.
But
Al-
epsilon,
always-
no, I mean, but epsilon is small. That's okay. Maybe
No, that means
epsilon
it's always
smaller than
okay.
1. Epsilon much smaller than 1. Epsilon is, I don't know, 10 to the minus.
This
52.
condition is always okay with the sin x. I think.
But
Because
you have here a fraction, and fraction has numerator and denominator.
okay.
What happens if the denominator is 0? Then fraction blows up to infinity.
The first one
Okay.
always if the
Can you find points then S2 blows up to infinity?
first time no,
Why not?
because sinus x double prime and sinus x it's always the same.
Yeah, but you have different power. So
This
q double prime is minus sine,
yes,
right? But here we have q to the 3 halves.
okay.
In total, we have 1 over q, square root of sine.
It's 0.
Why cannot be 0? It actually can. Right?
Yeah.
The same true for this one. right? So that's why we can claim that near x equals b times n, WKB approximation is bad. I mean, all physical optics, WKB approximation is bad. So we cannot neglect this term because it's not small compared to 1. Okay? We need to take more terms and find out whether they compare small compared to 1. Okay? So that was the first question. I mean, we can use WKB, right, in physical optics approximation, but far away from this point. Okay. So now, is WKB accurate for when x goes to infinity? Let's fix it. When x goes to infinity, you constantly cross this forbidden point, right?
The same.
So yeah, so that's why is not valid. You can't use WKB then x goes to infinity. Okay. This is for the first case, right? For the second case, you can see pretty much the same picture, but you have different points here. You have now square root of this. And x equals to plus minus square root of this thing. S2 blows up to infinity, and that's why you cannot use physical optic approximation close to this point. The same for the second question. Then x goes to infinity. WKB is not accurate because you constantly crosses this forbidden point.
WKB or the physical optics?
WKB. Okay. Now we have this problem. Epsilon y double prime equals to square root of x times y of x, and x is greater or equal than 1. So we need to calculate how small must be epsilon to have accuracy of the solution of 5%. Again, we're going to use physical optics. So first of all, to use physical optics, we need to calculate S0 and S1. In this case, Q of x is square root of x, right? Then S0 is plus minus integral t1/2 dt. So it'll be plus minus x to the 3/2 2/3. That's S0. Then S1 is minus 1/4 ln x 1/2, or minus 1/8 ln x. Okay. And to find what is the mistake, right? We need to ensure that this term is smaller than 0. Okay, so the condition is epsilon times S2 of x has to be much smaller than 1 for all x. So we need to find epsilon, then this is true. Or yeah, it's better to write it like this. Smaller than our 0.5. Okay, that's actually our mistake, our accuracy. So okay, to calculate S2, we need to use this equation. Okay, so S2 is integral plus minus integral q double prime. So q prime is 1/2 x to the minus 1/2. Q double prime is minus 1/4 x minus 3/2. Okay, now we have minus 1/4 x minus 3/2 divided by 8 times q2, q to the 3/2. So it will be x cubed. Okay, this is the first one. Then minus 5 times q prime squared. So 1/4 times x to the minus 1. And then divided by 32 times x to the 5th dx. Now when we're doing math, we should get 9/160 x to the minus 5/4. That's the answer. And now let's plug in. We have epsilon 1/, so 960 x to the 5/4 has to be smaller than 0.05 for all x, because this function is decreasing when x is growing. We can plug in here the smallest x, so x equals 1, and that function will have the greatest value, right? The bigger one. So, and that's why epsilon is smaller than 0.3. When we plug in x equals 0, we end up with this. So we can take every epsilon, which is smaller or equal than 0.9, and it will be sufficient to find the solution in the physical optics approximation with the mistake of 5%. Okay, so accuracy of 95%. Okay, the last problem for today is following. We need to check the validity of physical optics approximation as x goes to infinity. So to check the validity, what should we do?
Delta S to X.
Okay, should be
But you should
much smaller than,
epsilon square. No?
yeah, but you can guess what is the value of epsilon here.
1.
Yeah. In this case, epsilon is 1.
So it will be good only for x goes to infinity? Because we need epsilon to be small.
We need to check it. I mean, when we find the answer, we can speculate about epsilon, but by now let's assume that epsilon is 1, and we need to find whether physical optics approximation is good enough. So basically we need to show that S2 of x is much smaller than 1. And we need to show that S0 is much greater than S1 and S1 is much greater than S2. So those two conditions. Let's start with the S0, right? Q of x in this case is ln x ln x squared. Okay. So S0 of x is plus minus 1/2 ln square of x. Can you see it? So we have inside the integral ln of x divided by x times dx. So we can convert dx over x as 1, and that's how we can get ln squared. Okay, so then S1 of x is just minus 1/2 ln of q of x. So basically of ln of x squared minus 1 plus 1/2 ln of x minus 2. Okay, and then we can make it even simpler as minus, first term is minus ln of x, and the second one is minus 1 over 4 ln of x. So because we're interested in validity, then x goes to infinity, we can neglect this term compared to this one. Both are lns, but x as a linear function grows much faster than logarithmic function. So that's why we can neglect this and have s1 as just minus 1 over 4 ln x. Okay, then s2. For s2 of x, we need to calculate a lot of stuff. First of all, q prime of x. Q prime of x is it's 2 ln x divided by x squared times the derivative of 1. So it's 1 over x. Okay. Then minus 2 ln x squared divided by x cubed. I think I did it right. Again, then because x goes to infinity, you can neglect the first term compared to the second one. As here we have 1 squared, just 1. 1 square of x grows much faster than just 1 of x. You can do limits of the ratio of those and show it. Okay, and then the second derivative, q double prime of x of this, so minus 4 times ln x divided by x to the 4th, first one. Then the second one is plus 6 ln square of x divided by x to the 4th. Think like this. And again, we can neglect this one. Then we need to plug in all of this to the integral for S2. And eventually we'll have plus minus 1 over 8 ln of x. Again, in the leading order. I neglected all the terms that are small compared to this one. Now you can see that this condition is true. So S0, which is 1/2 1 square of x, is indeed much bigger than S1. So S1 is just 1 of x. There is 1 square of x. And S2 is also much smaller than S1. Because, again, here inside 1 we have linear function, here we have logarithmic function.
That's the solution of the integral?
Yeah. final answer for it. You have there another terms, but they are I neglect them compared to this one because x goes to infinity. But you can see that this is not true for any x. I mean, then x goes to infinity. It's not true, right? So, but what do you think for small x?
Small x.
Then I don't know.
It's undefined when you get 0.
No, you plug in some x, then you don't have a 0. I mean, you can play with numbers, okay, and probably there is some region for x. Then you can say that this is smaller compared much smaller than 1. So and by much smaller than 1, maybe it's like this or this. Okay. So basically, if you have this, it means that your accuracy is 90%. This is 99%. So that's why even then epsilon is 1, you can still use WKB, and in some regions of x, it yields the good approximation.
The agents that are not x goes to infinity.
Again, then x goes to infinity, this physical optics approximation is inaccurate. But who knows, maybe if you take also S2 and S3, maybe you will eventually for S4 you will have this condition. So, yeah. But for
And that's because you get epsilon equal 1.
yeah, if
Epsilon 1
but again, if I'll have
choose
epsilon,
epsilon 1 0.000.
yeah, but even though
Always
if
find
I have
this.
epsilon here, which is I don't know,
You always find smaller x.
h bar squared, yeah, some very small number. Again, then x goes to infinity.
Go.
This thing beats any small number. You see, so it's not a problem with the epsilon. It's a problem with the x goes to infinity. That's the point. Okay.
Thank you.
Okay, good. So that's it for today.
When you check the first term, it's supposed to be
I mean,
Yeah.
Yeah. Absolutely. For sure. Fine.